to this second part of the day, and the first talk is by Harvey on PCF-GAN and beyond.
Thank you. Thank you very much for the invitation and the introduction. It's my great pleasure to be here and talk about our recent work on the past characteristic function-based GAN model for synthetic time series generation. So let me start with the motivation of our work. Time series data are ubiquitous nowadays. The examples range from the computer vision data to the quantitative finance data set. So in the slides, you can see that the video data skeleton-based action sequence, as well as the time evolution of the limit order book, are all examples of the time series data. And in the past few years, we have all observed the significant rise of the machine learning algorithm across different fields. However, for the domains like finance and healthcare, there are many sensitive time series data. The data availability and sparsity has become a key bottleneck to limit the full potential of the machine learning applications in those domains. Generative models for synthetic time series generation provide a promising means to tackle this problem. So generative adversary network, GANs for short, are the powerful tools for the generative modeling for synthetic data generation. So let me briefly recap how the GAN model works. So it's mainly composed with two parts, the generator and the discriminator. So the generator aims to map the pre-specified noise vector to the target fixed distribution, while the discriminator focus on to quantify the discrepancy between the true distribution and the fake distribution. And usually the generator discriminator are parameterized by the neural network with the model parameters. And how to learn, how to generate the fake data is translated to train the good generator. And it's actually conducted as a min-max game. So when we fix the generator, we will optimize the discriminator by maximize the discriminator's model parameters by maximize the discriminator distance. When we fix the discriminator, we will optimize the generator's model parameters in order to minimize the distance, and we will do it in an alternative way. And when the optimization converges, and we hope that the trained generator can produce the high realistic synthetic data to mimic the distribution of the real data. So GAN model achieves the superior performance for the static data. However, it's still quite challenging to apply the GAN model for the time series data. First of all, as you can see that this min-max nature of the GAN framework is quite computational expensive. And for the time series data, the problem would become more profounding due to the potential high dimensionality of the time series and the complex spatial temporal dependency inherited in the time series. Moreover, in comparison to the static image generation, time series generation lacks the systematic evaluation framework to assess the quality of the synthetic data generation. The main objective of our work is to enhance the discriminator of the GAN model for the time series data by leveraging the rough path theory. So for people who don't know much about the rough path theory, it's a branch of the stochastic analysis and can be viewed as a generalization of the classical control theory to make sense of the solution to the control equation driven by very rough signal, even rougher than semi-martingales. And in this talk, I will explain to you how to design the better discriminator using the path characteristic function, which is a important object in the ramp path theory. And the result, and also based on the path characteristic function, we design the computational efficient PCF-GAN, which not only have the good theoretical guarantees of its discriminator, but also can achieve the state-of-art performance on several benchmarking dataset, even in comparison with the strong deep learning GAN model baselines. And the main strength of the PCF-GAN is its scalability. It can be applied to potentially high-dimensional time series generation. And in this talk, I will focus on the path space. So in practice, we observe discrete time series. However, in this talk, I wouldn't differentiate the discrete time series and the path. We always embed the time series into a continuous path by interpolation. And the advantage of doing so is to provide the unified treatment for the time series of potentially irregular sampling or variable length. Also, this continuous time view of the time series is more well-suited to the high-frequency stream data. So the key question about how to design the good discriminator for the time series data actually boils down to mathematical question. One is how can we represent the distribution on the path space, and second is how can we quantify the two distribution on the path space, which can be used as a discriminator for GAN training. So before diving into our PCF-GAN, I'd like to explain to you how the classical characteristic function can be useful for generative model for the RD valued random variable. So we all know the definition of the characteristic function. So here let X denote the RD value random variable. Then its characteristic function is a map which maps from D-dimensional vector to this expectation of an exponential term. And the expectation is taken under the distribution of X. So the characteristic function always exists, and it has uniqueness. So it determines the law of X uniquely without any regularity condition, in contrast to the moment generating function. Moreover, it has a uniform boundness, which means actually if we use a characteristic function for the GAN training, we don't need to impose the penalty term to in the loss function. So the characteristic function can be used to describe the law of the RD value random variable. Then in the literature, Arthur and the co-author proposed the characteristic function distance to quantify the discrepancy between two RD value random variables. So here let capital lambda denote the RD valued random variable. Then the characteristic function distance, CFD distance, between X and Y associated with gamma is defined through this equation. So here you can see that this is the expectation of the L2 norm of the difference between two characteristic function of X and Y evaluated at this random lambda, and the expectation is taken under the measure of gamma. It's not difficult to show that if the support of gamma is RD, if gamma has a full support, then this is the CFD distance of X and Y equals to 0 if and only if those two distributions are the same, and also it has uniformly boundness. And how can we use this this CFD distance for the GAN training, or the discriminator of GAN? So the idea is we parameterize this capital gamma by its empirical distribution, say a finite sample of lambda I with equal weights. Then the corresponding CFD distance between x and y can be simplified by this average. Then we will treat lambda I as the model parameters of the CFD-based discriminator. And when given x and y, we will optimize lambda I to maximize its distance. That's how we will use the characteristic function-based distance for the GAN training. So next, I want to explain to you how to extend this framework to the distribution on the path space. So to do so, the key question we need to address is how can we extend this exponential map when the x is a path. Actually, the raw path theory provides an answer to this question. That is the unitary feature of the path. To define the unitary feature of the path, we will need to introduce the unitary matrix group and the corresponding Lie algebra, and the definition can be found in the slides. So the Lie algebra is a vector space, but the group is not. And here the unitary feature of the path, x, is defined as the solution to this linear control differential equation. So intuitively, here let's say we have the integer m, and we have the path x is the path of bounded one variation, and the capital M is a linear map which maps from Rd to the unitary Lie algebra of the order m. So this this linear map M plays a role as the lambda in the classical exponential function case. And I will explain to you in a minute that why the unitary feature is a natural analogy to this exponential function. So the equation 2 is a linear control differential equation, and the solution always lives on the group, because the range of M lives in the Lie algebra, and hence the right-hand side of this equation will live in the tangent space of the unitary group. And the starting point of the solution y0 is given by the identity matrix. So we call the map, which maps from this linear map M to the UM of X as the unitary feature of X of the order M, where M is the matrix order. So we can show that the unitary feature of X of the O order can determine the path up to the negligible equivalent class. And also, this unitary feature definition can be extended to other matrix Lie group. So let's have a closer look at the unitary feature. Let's start from the linear path. So if we start from the linear path, actually the unitary feature of the path x could be calculated explicitly. That is nothing else but the matrix exponential of m acting on the increment of the path x. And then you can see the direct link with the classical case. When we choose a matrix order equals to 1, the linear path x can be fully characterized by its increment, that is Rd valued variable. Then we can see that the unitary feature of order 1 is exactly just the classical exponential function used in the characteristic function. Moreover, the unitary feature has a nice multiplicative property. Suppose you have the two paths x and y of bounded one variation. The unitary feature of the concatenation of x and y is equal to the matrix product of unitary feature of x and unitary feature of y. This property enables the numerical computation of the unitary feature of any piecewise linear path. So in the following, I'd like to add a few remarks and explain the intuition behind the unitary feature, why this feature can characterize the time series or the path. So let's start from the simplest case, the piecewise linear path. So piecewise linear paths can be regarded as a concatenation of each linear segments. And this exponential composed with M maps off from the RDE element to the unitary matrix. And due to the inclusion of the unitary group, it's easy to see that it should contain more information than the classical exponential function. And hence, it will determine this RD value x. And the unitary feature of the entire path is a product of the unitary feature of the linear segments. Then, thanks to the non-commutative matrix multiplication, it helps preserve the order information. So if we switch the order of the linear segments in the underlying path, then the unitary feature would change for some m. That's why in the high level, why the unitary feature can preserve the order of the events in the time series. Also, this multiplicative property can ensure that the corresponding unitary feature of the path lives on the group and enjoy the uniform boundness. And we implement the unitary feature as the layer which can allow the backpropagation. So the unitary feature could be regarded as a new neural network layer, which can be plugged into the general neural network, just like the recurrent neural network. So here, the input data is the dimensional time series, and on the then by default we embed it into the continuous path space by piecewise linear interpolation. And here linear map m theta is fully characterized by its linear coefficient theta, and the theta here is the model parameters of the unitary development layer. Given the m theta, we will get the corresponding unitary matrix. And to enable the backpropagation, we use the optimization method on the matrix Lie group, so-called the trivialization, so that we can calculate the gradient of the unitary development with respect to the time series. So once we think that the unitary feature is the nature analogy to the exponential function, then the path characteristic function is nothing else but the expected unitary feature of the stochastic process. In the literature, we can show that the path characteristic function satisfies it always exists, and it has the uniqueness as well as the uniform boundness, just like the classical characteristic function for the RD-valued random variable. And to turn the path characteristic function to the distance to measure the discrepancy between two distributions on the path space, we need to use the certain norm on the metric space. So here we will use a standard Hilbert-Schmidt norm on the metric space. Then we are ready to define the path characteristic function distance, PCF-D for short. So here you can see that it's very similar to the previous CFD distance. Here this curly M is a random linear map, which map from RD to the unitary Lie algebra U of M. And the PCF-D distance associated with M, act on X and Y, is given by the square root of the expectation of the L2 norm of the difference between two PCF-D of X evaluated at this curly M. And like the RD case, we can show the separation of the points uniformly boundless, as well as the Lipschitz continuity. So this theorem says that under certain regularity condition, the PCF-D distance between the fake distribution induced by the generator and the target, the true distribution X is Lipschitz continuous with respect to the model parameter of the generator. And this theorem can be used as a justification of the gradient-based optimization method in the GAN training. And like before, we will approximate this random linear map by its empirical measure. So now we have a finite set of the samples Mi. That's the model parameters of our EPCF-D distance to be optimized. And we will use the EPCF-D distance as a discriminator. And this collection of Mi empirical measure of the linear map will be learned from the data. And this is a flow chart to illustrate how the unitary feature and the PCF of the time series is calculated. Okay, so now we are ready to show the vanilla version of the PCF-GAN. So recall that the goal of the GAN model is, in this case, we aim to build the generator G theta to generate the target distribution to as close as to the real distribution X as possible. And the data set we have is multiple samples, ID sample from the true distribution X. And so we, to fully describe the GAN model, we just need to expand what is the generator, what is the discriminator. So generator here, we consider the noise distribution is the discretization of the Brownian motion. And the generator could be any sequence-to-sequence model. And as you can imagine that we will use the PCF-D distance as a discriminator. So when we fix the generator's model parameter, we maximize the linear map coefficients to maximize the PCF-D distance. And when we fix this random linear map characterized by theta m, we will optimize the generator's model parameters to minimize this distance, and we will do it in an alternate way. And to further enhance our model for the high-dimensional time series, we introduce the embedding, which can reduce the potential high-dimensional time series to the moderate dimensional time series. And the key question about embedding is it should preserve the essential information of the original time series. So mathematically, it means that we would like to have the embedding has an injectivity. Given the embedding, we can recover the original time series without much information loss. Therefore, we introduced the autoencoder structure with the embedding in our PCF-GAN framework. So here, we will make sure that the generator and this embedding map M are pseudo-inverse of each other. Then we introduce two additional laws to encourage that this injectivity and autoencoder structure of the generator. So here, you can say that we define the reconstruction loss by this mean squared error of the noise vector, and F composed with G act on the noise. So, and this is a sample-wise reconstruction. Implicitly, it will encourage the generator and embedding is the pseudo-inverse. Additionally, when the generative model is well trained, the latent embedding of the real-time series should be close to the pre-specified noise vector of the generator. Therefore, we will use the ePCF-G between the embedding of the true data and the noise vector as the regularization loss. And when this is equals to 0, it means that those two distributions are the same, which again enforce this pseudo inverse relationship between the generator and embedding. And we also have the corresponding training algorithm for that. Okay, so in the following, I'd like to show you some numerical results to demonstrate the effectiveness of the proposed PCF-GAN. So here we choose the full time series data. That is a raw volatility model, synthetic data generated by raw volatility model, the Google stock dataset, Beijing air quality dataset, as well as the EEG I-state dataset. And as shown in this table, those four datasets have quite different statistic characteristics. So the dimension range from 2 to 14, and the time dimension vary from 20 to 200. To benchmark our proposed method, we choose the three strong GAN models specifically for the time series generation. That is a core GAN, RC GAN, and time GAN. To give the comprehensive evaluation to assess different aspects of the time series generation, we use the three types of the metrics, that is the discriminative score, predictive score, and CMMD. So the discriminative score is about to assess how easy to distinguish the true data and fake data. So we will train a post hoc classifier to classify the real data from and the fake data. The lower accuracy means the better quality of the generative model. The predictive score is used to quantify the utility of the synthetic data. The good synthetic data should be useful as a surrogate to the real data for the learning task. So here we consider the regression problem to use to predict the second half of the time series using the first half of the time series. And we will train the model on the real data, test on the train the real data, test on the real data, and we will also do the train on fake data and test on the real data. So the similar performance on the tested data set demonstrates the better performance. The last test metrics is a CMMD. That is a generic test metric on the distribution on the path space. So this is a sample plot of the real data generated by the raw volatility model, and also the sample plot of the fake data given by the different GAN model. So visually, you can see that PCF-GAN and time GAN outperform the other quite significantly. So for the low dimensional time series, you probably can judge the performance from those plots. However, for the high dimensional time series, it will be very hard, and we should use the quantitative test metrics to assess the performance. And here you can see that across the four data sets, our proposed PCF-GAN outperforms the baseline significantly. And the time GAN, among the three baselines, time GAN is the only one which also has the autoencoder structure and allows to reconstruct the time series from the embedding. So we also use those three test metrics to assess the reconstruction utility of our model compared with time GAN. Again, our model consistently outperforms time GAN. And if we look at the reconstructor sample plot, So here the left panel is a sample from the real data. And then we plot the so if we know the embedding and apply the GAN model to reconstruct it, so the reconstructed path from the PCF-GAN is in the mid panel, and the left panel provides a result for the time GAN. So clearly that the PCF-GAN is better in terms of capture the shape of the time series. And also those additional two loss functions can help us monitoring the training performance of the GAN model. It's well known that GAN model is difficult to train, and the discriminator generator loss is very oscillatory. And those additional two loss functions indeed can help us better understand the performance of the training. So to sum up, so how many minutes do I have?
About 15.
Okay. So to sum up, the path characteristic function is a faithful representation for the law of the random variable on the path space. And the distance, the PCF distance, are proven to have the good theoretical property, that is a characteristic uniformly boundness and differentiability with the model parameters, which are useful for the GAN models for the time series generation. With incorporating the embedding layer as well as the autoencoder structure, the PCF-GAN stabilize the training process and consistently outperform other baseline model on several benchmarking data set. It shows the potential on the more complex empirical data set. Moreover, I want to stress that this autoencoder structure of the PCF-GAN enable us to have this additional reconstruction functionality on the time series. So in the following few minutes, I want to briefly talk about the more recent development based on the PCF-GAN model. So first of all, although the PCF can characterize the distribution on the path space in the distribution sense, however, it cannot well capture the conditional law. So what I mean is that even we know that two process has very small PCFD distance, we cannot guarantee that the conditional law of the two process given the filtration FT is close. So in other words, it might not be close in the extended weak topology. So to solve this problem and further enhance the discriminative power of our GAN model, given the stochastic process X, we also consider its prediction process, that is the conditional law of X given the filtration FT. So that is a measure valued path. And for each conditional law, this is the measure on the path space. We can use a path characteristic function to represent this measure. We will automatically have metrics evaluate the stochastic process for certain linear map. And we will use another path characteristic function to characterize the evolution of this prediction process. And that is so-called our high-rank PCF. And we also design the computational efficient algorithm to facilitate the application of the high-rank PCF to the GAN modeling. And secondly, in the chapter and lines of work, it's the PCF can determine the law of the unparameterized stochastic process or signature is proved. However, that proof is not constructive, and it's not clear that whether we do need all the PCF information to characterize this law. So in our recent work, we provide the alternative constructive proof for this statement. And also from this proof, we have the byproduct. We actually can demonstrate that under certain regularity condition, the sparse version of the PCF can characterize the law. So sparse version of the PCF, it means that the PCF evaluated as a sparse subset of the linear map. And in fact that we only need to consider the linear map in the set showing in this red block. And here you can see that it's only have the dimension which is the same as the matrix order. However, the original unitary Lie algebra has the order is the matrix order power 2. So it really reduces the dimensionality significantly, while this restricted PCF still have very good characteristic. The last but not the least application is we can use the PCF for enhancing the generative model to generate the high quality conditional law of the Levy area given the Brownian motion. So it shows the possibility of applying the PCF beyond the time series data. So what we do is the Levy area is a static variable. We embed it into the linear path, and we still use a PCF-D distance as a discriminator. But of course, we did a lot of design about the generator by better incorporating the property of the Levy area. And we can see that using the PCF of the high order indeed improves the performance of the Levy area generation, which has the promising application for accelerating high order SDE simulations. Yeah, if you are interested in knowing more work of my research group, and there is a link. So I think I would like to stop here for now. Thank you very much.
Yes.
So when you calculate the PCF, I think you maximize over random linear map. So does your results with Jiajie, does that mean you just need to maximize over random linear map that are supported on these sparse sets?
Under some regularity condition. So when the expected signature decays sufficiently fast. Yeah. Otherwise, I think so. Without a regularity condition, we don't need a unitary group. We need a SO group.
So, and why do you need the fast decay for expected signature?
Because the way we prove this characterization, this sparse version PCF to determine the law is through this sparse version of PCF determine the expected signature. Yeah. If we don't assume that assumption, we can improve the original result from unitary group to SO group. So that is improvement like a factor of 4.
If I understood correctly, your path correlation or characteristic function should kind of capture the correlations along your path. Is there any way to calculate, say, the temporal variation of the covariances, respectively of the correlations directly from your PCF?
It's a very interesting question. So what I know is that I think if we consider PCF of certain path transformation of the original time series, the Lie transformation of the original time series, I think I could demonstrate how it characterizes. Yeah. But directly, without this embedding, this transformation, so in theory, it should characterize the correlation, but I don't know the constructive way to how to show that.
And so what happens if you have crossbreeds between fake data and real data? So if you have some parameter that and at some points you have fake data, and then you have real data and fake data, and then you control the ratio between them. How can you anticipate?
So the data set is composed with the samples under the true measure. That's something we cannot change. The generator, the fake data, you can use your generator to simulate as many as you want.
Yeah, it's more just if you have mixtures, I mean, just like a real application and trying to.
Well, I think one useful utility of this synthetic data generation is to augment the original data, so that you can use it to train the complex deep learning algorithm without the overfitting issue. But we didn't test that, but rather for the most similar, the test metrics most closely related to what you said is this a predictor score. But in that case, we only use a fake data to replace the real data.
Quick question for me. So you have this measure n.
Yeah.
Where is it coming from? Is it a choice, and how robust is the results?
So this linear map M. So first of all, the matrix order M is a hyperparameter to truth. So once we determine the matrix order M, then the linear map M is always from the RD. That's the path. The D is a path dimension to the Lie algebra of the order M. Then this linear map M is learned from the data. So because we have this loss function, so we will choose Mi in order to maximize this distance, rather than we pre-specify what M is. But for the small data case, we can also do random sampling. You pre-specify what is the random distribution of M is, and you random sample sufficiently large number of linear map M. Then the resulting PCF-D distance is supposed to also have the good discriminator power, as long as the original distribution has a full support.
Okay, so let's thank the speaker again.